Hi chemistry students. This tutorial is going to be about doing an equilibrium problem in a chemistry class. And the key thing here is that it's not the most difficult problem in the world, but it has all the key elements that you'll always need to follow when doing any equilibrium problem. So if you can do this, if you understand this particular example, then you can do any equilibrium problem tossed at you if you're just very systematic and you understand where everything goes. So let's try the problem and see if it helps out. We're going to look at the decomposition of silicon monoxide in the gaseous form to form liquid silicon and gaseous molecular oxygen. It's got an equilibrium constant of K sub C equals 0.962. And there's a nice interesting thing here. Since this is K sub C, that means everything deals with molarity concentration units. If it was K sub P, we would be doing everything in pressure, atmospheres. All right, so what it asks is, what's the equilibrium concentration of the silicon monoxide when this system reaches equilibrium? In other words, if they put 50 grams of each one of these substances, 50 grams of silicon monoxide, 50 grams of the liquid silicon, and 50 grams of oxygen gas, if they put that in a 2-liter container, what will be the end result when we reach equilibrium in terms of the concentration of the silicon monoxide? Since this is an equilibrium, we must make sure we have the proper equilibrium expression, which is simply that the equilibrium constant K sub C is equal to the concentration of the O2 divided by the silicon monoxide squared. Two interesting points. The squared comes from the stoichiometric coefficient right here. And we've ignored the silicon liquid because it's a liquid. And we're always going to ignore liquids and solids when we do our equilibrium problems. All right, so before we can do anything towards solving the problem, we need to get our initial situation in terms of concentrations, because this is a K sub C, or an equilibrium expression in terms of concentrations. So we can solve that quite easily by looking at the number of moles per liter that we're looking for in terms of silicon monoxide, starting with the 50 grams in a 2-liter container and converting with the molecular mass of silicon monoxide. We find the concentration of the silicon monoxide. And similarly, we can do the same thing with oxygen, O2. So we now have the initial concentrations of these two species. We could calculate the initial concentration if we wanted to of the liquid, but that's not necessary because it's not in our equilibrium expression. So don't waste time doing that if you don't have to. So what we'd like to do is we'd like to write an ICE table down and initialize it by putting in what we know. So what we know right now is just these initial concentrations. Important point for you is I write the entire reaction down again, including the liquid and the phases, all the phases, and including the substance that's a liquid. You may say, oh, I just want to ignore it, but don't, because we want to make sure that we have a full reaction there. Here for the initial concentration of the liquid, because I don't care, because it's not part of my equilibrium expression, I'm going to just put some lines in there, or a line, to just remind myself not to deal with it. So once we're here at the initial state, we need to determine which direction we go. To do that, we must compute the reaction quotient, Q, and then once we have Q, we can compare it to K. So if we do that, we find that Q is equal to 2.43, and since K was equal to 0.962 that was given to us, when we compare them, we see that the K is less than the Q. The equilibrium constant's less than Q. And whenever that's the case, we're going to shift to the left. In other words, our equilibrium requires us to have less of the product and more of the reactants than what we currently have. So let's shift to the left. And the way we do that is we realize that if we're moving left, all the products are going to decrease in concentration, and all the reactants are going to increase in concentration. So that means the products are going to have a negative X, and the reactants will have a positive X. In this particular instance, it's negative 1X, because the stoichiometric coefficient right here for the oxygen is 1, and it's a positive 2X for the silicon monoxide because of the stoichiometric coefficient there being a 2. We fill that in, and we now have our change part of our ICE table all set. It's easy to complete the ICE table because all we do now is we add this column and add this column to find the expression for our equilibrium concentrations. As simple as pie. So now that we have this, what can we do? Well, we know the equilibrium expression is K sub C is equal to the concentration of the oxygen divided by the concentration of the silicon monoxide squared. Well, we have, from our ICE table, an expression for this in terms of the initial concentrations and the change. We have a similar expression for silicon monoxide in terms of its initial concentration and the change. And we also know what K sub C is. Since the change is all in terms of one variable, we can set up an equation now that's solvable. We've got a very simple mathematical, algebraic fun time for us to go through to solve for x. But there's one equation and one unknown, so it can be done. Let's see how that works. It's very simple. Here's my equation for my equilibrium expression. I first multiply over to get the denominator of this fraction out. And then I take this square and I get rid of it by expanding this function. Then I distribute the 0.962 throughout. I rearrange and solve, and I get here in red a quadratic equation, which is in the characteristic form of a times x squared plus b times x plus c. Notice in this case, c is a negative number. So if we want to solve the quadratic equation, it's always minus b plus or minus b squared minus 4ac divided by 2a. In this particular case, because we have a negative number right here, our only option to get a real answer, a physically real answer for x, is just to add. So we can actually skip the subtraction part. However, if this is not a negative value, you need to take into account both possibilities. So if we plug these numbers into our calculator, we get 0.128 as our x. Now, a lot of people think that's where the problem ends, but the question asked us to solve for the concentration of silicon monoxide. And that's not x. X is the change in the oxygen, so in the oxygen concentration. So we need to actually go back to the expression for the equilibrium concentration of silicon monoxide, which is actually 0.567 plus 2x. Plug in our x, and we get 0.824. So there you have it. That's how you solve an equilibrium problem. I hope this helps keep you on track and getting ready for all the equilibrium problems you'll see in the future.